So these last two topics aren't covered in chapter 5. They're covered in other chapters, and they're actually applications of something that you are somewhat familiar with. So these last two are actually probably easier than the ones in the previous videos. So today's topic is all about bond enthalpy. And this is how we were able to calculate delta H last year by doing by using the formula that the sum of the bonds broken minus the sum of the bonds formed, and looking at the enthalpy of those bonds. So what is bond enthalpy? Well, bond enthalpy is defined as the energy it takes to break a covalent bond or the energy released when a covalent bond is formed. Remember that a covalent bond, it fulfills each other's octet. The negative electrons of one are attracted to the positive nucleus of the other, so that releases energy. Those atoms are more stable when they are bonded together. What relationships can you see from this table? So if I take a look at, let's say, these guys here, so the triple, those are all single, double, triple bond, and here's carbon-carbon, single, double, triple bond. You should be able to notice a few general trends. And so the first one is that triple bonds have a greater bond energy than double or single. So basically the more bonds is higher bond energy or bond enthalpy. And according to Coulomb's law, that sort of makes a lot of sense, right? That the force of attraction is greater when there are greater charged particles, or the particles have more charge. So when I have a carbon-oxygen triple bond, that's the sharing of 6 electrons. And that is going to take an awful lot of energy to overcome, especially as opposed to a carbon-oxygen single bond where you are only sharing 2 electrons. The other generality that you may notice is, in general, and there's exceptions to this, but in general, the smaller the bond, the larger the bond energy. And the longer the bond, the lower the bond energy. And that is another example of Coulomb's law. So here we have that formula. The energy change in a chemical reaction can be estimated as, and I'll talk about that in a second, the sum of the energies of the bonds broken minus the sum of the energies of the bonds formed. And then there's that formula there. Where students get confused is because we have done delta H with the delta H's of formation, and that's products minus reactants. And this is broken minus formed. This is kind of reactants minus products. And so that can be very confusing because you are kind of switching it around. But think about what this is literally trying to convey. Actually, I'll go to this picture. Right? What this is saying, bonds broken minus bonds formed, was that this is the energy that needs to be put in to break a carbon-hydrogen bond and a chlorine-chlorine bond. So that's energy in, so that's positive. And then the energy that is released when these 2 new bonds formed, that's energy out, and that's negative. So that's why it's bonds broken minus bonds formed. If we go back to this table, this is a table of average bond enthalpies, and an important piece of this is average. The strength of a bond is dependent upon what molecule that bond is in. Like, what else is that one of those atoms bonded to? So for example, the carbon-hydrogen bond, So for example, the carbon-hydrogen bond is listed at 413. But what if this carbon is also bonded to an oxygen and another carbon? What if it's bonded to 4 or 3 other carbons? Right? What if it's bonded to 3 chlorines, very electronegative element, pulling the electron density away. So that's why this says average. In a specific molecule, it would be a more specific answer. Okay, sample exercise 18.12 is using these average bond energies to estimate, you can see they're using the word estimate there, estimate the delta H for the combustion of this reaction. So, here's the formula. Delta H of the reaction is equal to the sum of the bonds broken minus the sum of the bonds formed. And so I have to really go and take a look at that chart and make sure that I'm keeping track of the bonds that I'm breaking. So in the bonds broken, it's 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds, but I do need to account for the coefficients here. So I don't have to break 6 carbon-hydrogen bonds. I actually have to break 12 carbon-hydrogen bonds. And I also have to break 1 carbon-carbon bond, carbon-carbon single bond, and then 7 oxygen-oxygen double bonds. So those are all the bonds that I need to have broken. And then the bonds formed, remember, it would be 2 carbon-oxygen double bonds times 4. So that's 8 carbon-oxygen double bonds and 2 oxygen-hydrogen single bonds in that molecule, but 2 times 6 is 12 oxygen-hydrogen single bonds. So now I just go to that table and start substituting the numbers in. So the answer comes out to be negative 2,831 kilojoules. And I said per mole of reaction because that's what happens each time this reaction that is depicted happens. So that's what happens when 2 moles of ethane, 7 moles of oxygen, 4 moles of carbon dioxide, and 6 moles of water are used. So it's not for 1 mole, it's not the combustion of 1 mole of methane, it's the combustion of 2 moles of methane. So that's why we just said moles of reaction. And then, I always double check these, make sure that, it should be a negative number because it is in fact a combustion reaction. So it should be exothermic. So this integrative exercise here has a bunch of different pieces of stuff that we have learned before. So I'm going to let you guys work through this on your own and just give you some of the answers. So it says phosgene, a substance in poisonous gas warfare during World War I, is named because it was first prepared by the action of sunlight on a mixture of carbon monoxide and chlorine gases. Its name comes from the Greek word phos, which means light, and genes, which means born of. Phosgene has the following elemental composition, right? This is the percent by mass, and then here's its molar mass. So what that means is that you would need to in order to find the molecular formula, you have to do that empirical formula to molecular formula. Convert from percents, assume 100-gram sample, convert to moles, divide by the lowest number of moles. The answer for this is COCl2. Okay. After that, you have to draw 3 Lewis dot structures for these that satisfy the octet rule for each atom. You are going to have to make some double bonds in there. Using formal charge, determine the Lewis structure that is the dominant one. So for formal charge, remember that's valence minus assigned. That's how you calculate formal charge. And then D, using the average bond enthalpies, estimate delta H for the formation of gaseous phosgene from carbon monoxide and chlorine gas. Write a balanced chemical equation, do bonds broken minus bonds formed. I got negative 141 kilojoules. Okay, so try those out and we'll check our answers in class.